Today we will start a new topic which is very important: how to design steel, concrete, composite beams. Just a reminder, last semester we learned if you have concrete beam with steel reinforcement area steel, we learned how to design this beam, how we can assume this width, how we can assume the thickness, how we can figure out the required area steel, and how we can convert it to number of bars. We learned all of this stuff last semester for reinforced concrete beams. And also in this semester, few weeks ago, we learned if this beam is steel beam. Steel beam. We learned how to figure out phi mn and how to make sure the m ultimate is smaller than or equal phi mn. So we learned before the design of reinforced concrete beam and the design of a steel beam. But today we will design steel, concrete, composite beams. Okay, I have question. We know concrete is excellent in compression. Steel is professional in tension and professional also in compression, but we have issue with buckling. So we can say steel is professional in tension. For steel, for reinforced concrete, and we have steel reinforcement, let me explain it for you. What is the benefit to use steel concrete composite beam? Do you remember this story? We have neutral axis, the concrete above the neutral axis under compression, so it works. The concrete under the neutral axis under tension, so crack occurred. So the stress distribution will be something like this. Here is the compression value C, here is the tension value T, and the strength of this cross section depends on this C and this T. That means the strength of this cross section depends on the part of concrete only above the neutral axis and the steel reinforcement only below the neutral axis. One of you will say, hey, what about this concrete? Useless. No contribution in the strength of the cross section. Actually, we have another function for this concrete, keeping this reinforcement working with this part of the concrete. It's not our part right now, but the concrete below the neutral axis is cracked, useless, does not work, does not contribute in the strength of the cross section. Okay, what do you think if I can put concrete only at the top and the steel beam at the bottom, and I will keep neutral axis in between or at least above a little bit? So if you have bending moment, the upper part of the cross section under compression, excellent, we have concrete. The lower part below the neutral axis under tension, excellent, we have steel. So this cross section is more efficient than this cross section. So sometimes we are looking for a steel concrete composite beam. This composite beam can be, like I said, the concrete slab connected to steel beam to make sure you have neutral axis in between, and the concrete all the time under compression and the steel all the time under tension. This is the common type of composite beam. Sometimes, for me, I don't prefer it. Sometimes we have steel beams fully encased in concrete, like this one or like this one. I believe the only benefit behind this shape or this shape, you are protecting steel beam against fire. Against fire. But for this one, no, the first at the first time of the fire, the steel beam will be exposure to fire. So we have two types of beams. We will cover only one type, which is the common one. The first one is steel beams fully encased in concrete so that the natural bond between the two material holds them together. Bond, we have bond, but this bond is not strong enough. Anyway, and encased the steel beams attached to the concrete slab, steel beam attached to the concrete slab, solid or formed steel deck by mechanical anchors. Can you see this anchor and this anchor, which is repeated at uniform spacing? Shear connectors. In this chapter or this part, only the more common second type is discussed, which is an encased steel beams attached to the concrete slab. Anybody has any question so far? Yeah. Anybody has any question so far? And also one more thing, Brock, this one, composite, guys, let me say that composite meaning of composite. Composite means we have two materials. But for these two materials to work together, they must be one unit. So if you have concrete and you have steel, how can I make the two materials working together as one unit? The first type of beams depends on the natural bond between the surface of steel and the surface of concrete. I think this natural bond not strong enough. I think not strong enough to make the two materials working together as one unit. We will have problems. We will have issues between the two, especially the surface of the steel is smooth. So the connection or the bond will be weak. But this one, can you see this anchor? I will show it to you later. This anchor has head, and the concrete will board around it. So I believe we have mechanical bond or mechanical interaction or mechanical composite between concrete and the steel beam. Anyway, we covered this part last semester. If you have a steel beam and another steel beam, and another steel beam supporting one concrete slab. So this beam has part of the concrete slab working with this beam alone. This width can be called effective width. Be effective. I think we covered something like this last semester. So we have effective width for each steel beam, which is given by the following equation. The smaller of span divide 4 or center line to center line. I'm sorry. Yeah, this beam and this beam, we have center line in between. This beam and this beam, we have center line in between. So this distance S can be the effective width. Or this beam has a span L divide 4 can give you the effective width. Which one I'm gonna use, S or L divide 4? I'm gonna use the smaller value. Does that make sense? That makes sense. So I believe the first step, we need to figure out what is the cross section. We have cross section, steel beam, concrete slab supported by steel beam. So what is the width of concrete which is working with steel beam, which called B effective? Span divide 4 or S, which one is the smallest one? Let me repeat this story one more time. The best scenario that the neutral axis will be within the concrete slab. So this part of concrete will be under compression. .85 F prime C at depth A, and the depth of the neutral axis is C. Anyway, we have compression here. This compression equal 0.85 F prime C P effective time A. The lower part below the neutral axis, we have part here of concrete, I believe, but this part is ignored, cracked, concrete cracked. So this part of steel will be under tension F field, and we will have tension here T. This T equal area gross of this steel beam time F field. From equilibrium, C equal T. If you apply summation F of X equals 0, this force will equal to this one. So 0.85 F prime CP effective A equal area gross F field. I believe the only unknown in this equation will be the depth of the stress block A. So the nominal moment, if you take moment here or take moment there, will equal T time this distance in between. This distance from this figure equal depth of the steel beam plus this distance to the center of the concrete under compression. Or if you assume this total depth is h, I can say equal area gross time F yield. This term is tension T time the total depth minus A divided 2. Anyway, but by the way, this distance is the distance between T and C. Once you get nominal moment, you can multiply it by phi Mn and phi equal 0.9. And make sure the design philosophy is M ultimate is smaller than or equal phi Mn. So how can I design composite beam? We will assume the concrete slab thickness. And we will assume a steel beam. Then we need to figure out what is the P effective. And we will do the scenario. The neutral axis will be within the concrete. This one will be under compression. We have capital C. This one will be under tension. We have capital T. The capital C equal 0.85 F prime C P effective time A. Capital T equal area gross of this steel beam time Fe. For acrobium, both of them are equal. So T equals C. I can figure out the distance A. Then I can figure out the nominal moment. Guys, we don't recommend to have this cross section. Your thickness of the concrete slab is small, so the neutral axis will be within the steel beam. We don't like this. Do you know why? Because this part, concrete, will be under compression, and the steel will be on this part of steel will be under compression by F yield, and this 1.85 F prime C. So we have two parts under compression, concrete and steel, and the remaining part of the steel beam will be under tension. One of you will say, hey, what is the problem in this scenario? Is it wrong? I didn't say this. It's not wrong, but we don't recommend. Do you know why? Because as I told you, we have concrete, which is excellent in compression. And we have steel, which is excellent in tension. So why you are using part of the steel under compression? We don't like this. And remember, steel is very expensive in comparison to concrete, very cheap. So go ahead and increase the thickness of the slab to make sure this neutral axis in between or even inside the concrete slab. That makes sense? So I didn't say it's wrong, but we don't recommend. We would like this shape. Any question? To make sure this concrete slab is working compositely with this steel beam, we must provide shear connector. By the way, if I draw this steel beam, like this, So this shear connector can be probably one row, like this, or 2 rows, like this. And what is the spacing? How many? All of these questions we need to answer. So by the way, shear stud connectors looks like this one. We have shank and we have head. You must have head. And this one is connected or welded to the top flange of the steel beam. We have some rules here. Before going through these rules, I would like to share this video with you. I think I shared it one time before, but let me do it one more time. How we can weld the shear connector to the top flange of the steel beam. We have gun, special gun called Nelson gun. This gun will weld the shear connector to the steel beam. Camera or video? Video. Boring of concrete. Here is the steel beam, here is the shear connector, and here is the formwork prepared for boring of concrete. This is some instrument called strain gauge. It's not our topic. Steel reinforcement. We will put the steel reinforcement. Boring of concrete, slump test, curing of concrete, cylinders. Here is the final shape: concrete connected to steel beam with shear connector. So the most important part is the first part. How we can weld this shear connector to the steel beam. It's very easy. This tool called Nelson gun. Nelson gun. Any question? Any question? So this one or this number of shear connectors, you can do it a few minutes. Each one take 10 seconds or 20 seconds or whatever. So you can finish any number you want. We have some rules. Studs for use with composite construction must be manufactured according to ASTM A108 steel with ultimate tensile strength F ultimate 65. Diameter of this studs, of these studs, 3/8, 1/2, 5/8, 3/4, 7/8, or even 1 inch. These diameters are the commonly available diameters. Stud diameter shouldn't be greater than 2.5 times the thickness of the flange to which studs are welded. This steel beam has flange, and the shear connector will be welded to this flange. The standard said the stud diameter, this diameter, shouldn't be greater than 2.5 times this thickness. T flange and this diameter. So diameter is smaller than or equal 2.5 T flange. Studs must be uniform diameter. Be headed. We should have this head. And I have a chamfered weld ends. Anyway, any questions so far? So these rules just for restriction, limitations about diameter, about the thickness and the diameter, the relationship between the thickness and the diameter, all of this stuff. How we can weld this shear connector by the video in this link. Okay. Guys, looks like I have a technical issue here. So just a second. I will restart my laptop. Just a second. Don't go away. So I'm back. Sorry, guys. Okay. So the question is, how can we figure out the required number? How many? How many? So the number required, n equals summation qn divide qn. What is the value of the numerator? Summation qn equal area gross time F yield, which is T. Do you remember the value of T? It will be the numerator. What about the denominator? Qn. Qn is the nominal shear strength of one stud. How can I figure it out? Using this table. This table based on the diameter of the anchor and the F prime C of concrete, I can give you what is the value of Qn. So Qn from this table. Qn from this table based on what is the diameter, what is the F prime C of concrete, and if you have normal weight concrete or lightweight concrete, and if you have concrete steel deck or no deck. We will cover this table next meeting. But by the way, make sure the required number n is the number of shear connectors between the maximum positive bending moment and the adjacent zero moment. I'm sorry, what you mean by this? Let me explain it here because it's very important to understand this point. It's very critical. We have a beam like this. This beam under the effect of uniform distributed load. Anybody can tell me or remind me what is the shape of bending moment? I think the bending moment diagram looks like parabola. The maximum value here equal WL square divide 8. That's right? Okay, we have a section here. This section, maximum moment. And this point, zero moment. Between this section and this section, we need number of shear connectors equal to this value. So the number of shear connectors between the maximum positive moment and the adjacent zero. So the number here, for example, 36 connectors. That means in this half of the beam, we need 36. The other half of the beam, we need 36. So the total number of connectors along the beam will be 72 connectors. So guys, please, N, not the total number of shear connectors required, but the number of shear connectors required between the maximum positive moment and zero moment. Or if your beam is continuous, so your bending moment diagram looks like this. If you would like to figure out what is the number of shear connector in the negative moment, okay, between the maximum negative moment and the zero moment, between this point and this point, we need capital N. So keep in your mind, this equation will not give you the total number, but will give you the number of shear connectors between maximum positive or maximum negative and zero moment position. How can I figure out this number? Equal summation Qn divide Qn. Summation Qn equal area gross of the steel beam and time F yield. Qn, which is the denominator, which is the nominal shear strength of one shear connector. How can I figure it out? Using this table based on the diameter of the shear connector and the F prime C, the type of concrete, normal concrete or lightweight concrete. Anybody has any question? Do you have any question? We have one example here. I will cover this example next meeting. We need to design everything, how many shear connector, this beam is adequate or not, safe or not safe. We will cover all of this stuff next meeting.